series on knots and handlebodies.
Okay, thank you very much. It's a great pleasure to be here. It's my first time in Cambridge. And you know, I saw a YouTube video about how Newton measured the speed of sound. I don't know if maybe everybody knows this, but you know, there's a courtyard in Neville's Court courtyard in Trinity College, and there's this big colonnade, you know, a big walkway, and he measured the speed of sound, you know, which was pretty incredible. He measured the speed of sound by clapping, you know, and then hearing the echo. So you had to measure the time, you know, difference between when he clapped and the echo. And so he used, you know, the technology, the very recent technology of knowing that the length of the pendulum is proportional, square root maybe, the length of the pendulum, no. Well, anyway, you can measure the time from the period, you know, the period of the pendulum is proportional to the length of the pendulum. And so he kept, he would clap, and then he had a pendulum, and he'd see when the period matched the return of the echo, and then from the length, you know, he kept shortening it, and then from the length he could compute the time. So that's how he measured the speed of sound. I think he was fairly accurate, maybe within 10% or something like that. But anyway, so I'm looking forward to going down to Neville's courtyard and trying that. Okay, well, yes, I'm going to talk about boundary-reducing surgeries on handlebodies. And so the question is, when does Dehn surgery on a knot in a genus G handlebody yield a handlebody again? So a handlebody is the simplest manifold with a genus G boundary. And so if you do surgery on a simple manifold and you get a simple manifold, you'd hope that the knot was simple, and in particular that you could classify such knots. So this is an example of that. So let me just go over some notation, because it's different than what's been used previously. Let's see here. So I'm going to denote a Dehn surgery by K parenthesis alpha. So that means the Dehn surgery on K, on the knot K, along the slope alpha. So remember that Dehn surgery is removing a solid torus, removing a neighborhood of a knot from a 3-manifold, and then gluing the solid torus back in so that the meridian is some slope on the boundary of the knot exterior. Alpha is that slope. So the Dehn surgery is defined by the slope along which you attach the meridian. And so in our case, the ambient manifold is always going to be a genus G handlebody, so I'm not specifying that. Oops. And then so for a framed knot, we can parameterize the slopes. So the slopes are just unoriented isotopy classes on the boundary of a knot exterior. And you can parameterize the slopes by P over Q if you have a framing of the knot. And so 0, 1 means the framing slope, and 1 over 0 is the meridian. So for example, K sub 0 means that we're doing the Dehn surgery along the framing curve for a knot in the handlebody. And then one more definition, the distance between two slopes. So let alpha and beta be simple closed curves in a torus. In particular, I'm thinking of the boundary of a knot exterior. And then the distance, delta alpha beta, is the intersection number of those two curves on that torus. Okay. So, well, first let me give some examples of knots in manifolds with boundary, or at least in a handlebody that gives a handlebody back. The first example is a knot in any 3-manifold with boundary such that admits surgeries that give you the manifold back again. And so if you just take a knot that's parallel to the boundary of the manifold, and you do 1 over n surgery where you're using the framing coming from the boundary, then you get the manifold back again. And the argument is, well, so the knot is parallel to the boundary, so there's an isotopy onto the boundary. The trace of that isotopy is an annulus. So that annulus you can think of as embedded in the exterior of the knot in this manifold. And so you get a homeomorphism of the knot exterior to itself by twisting along the annulus. that twist takes, say, the 1 over n curve, the 1 over n curve to the 1 over 0 curve, and so you can extend the map on the exterior to a map on the Dehn surgered manifold. Since it sends the 1 over n curve to the meridian, it sends the Dehn surgery to the original manifold. So you know that the 1 over n Dehn surgery on such a knot is homeomorphic to the manifold again. So that certainly works for a handlebody, but that works for any 3 manifold. So let me give a more specific example to handlebodies, and this is due to John Berge. First, if you have a simple closed curve on the boundary of a handlebody, it's called primitive if there's a disk properly embedded in the handlebody that intersects that curve once. And the 2 things you need to know about primitive curves on the boundary of a handlebody is that a primitive curve is isotopic to a core of the handlebody. And the other thing is that when you attach a 2 handle along a primitive curve, you get, primitive curve on the boundary of a handlebody, you get a handlebody back again. So John Berge constructed some examples of knots in handlebodies that admit handlebody surgeries in the following way. He said, well, take 2 primitive curves on the boundary of the genus G handlebody that intersect once, then take a neighborhood of take a neighborhood of the union of those 2 curves, and then attach a 2 handle along the boundary of that neighborhood of these 2 curves. That's a manifold with 2 boundary components, a torus boundary component and a genus G boundary component. And then you can see that those are, well, it's the exterior of a knot in a handlebody, because if you fill that manifold, if you do a Dehn filling along alpha, then that's the same thing as attaching a 2 handle along alpha to this handlebody, so you get a handlebody back again. So 1 filling gives you a handlebody, and similarly, if you do a Dehn filling along the other curve beta, you get a handlebody. So this turns out to be a knot. This is the exterior of a knot in a handlebody that admits a non-trivial handlebody surgery. So that's a more or less trivial example. So I want to talk about bridge number of such knots. So I need to talk about a Haggard splitting. For us, a Haggard splitting of a handlebody is going to be just, well, a Haggard surface is just going to be the boundary pushed slightly into the interior of the handlebody. And then I'm thinking of that as kind of a generalized Haggard splitting, where a Haggard surface divides the manifold into 2 compression bodies. So in this case, it's a handlebody on one side and a surface cross I on the other side. So I'm thinking about that as a Haggard splitting. And I want to, given a Haggard splitting, you can talk about a bridge presentation of a knot in the manifold. A bridge presentation is one where the Haggard, on one side of the, you isotope the knot so that on one side of the Haggard surface, well, on each side of the Haggard surface, you just get boundary parallel arcs, or bridges. And so that's a bridge presentation of a knot. And then the bridge number is the smallest number of bridges that you can represent a knot. The smallest number of bridges that occur in a bridge presentation for the knot. And I'm going to denote, so we're going to take the boundary of the handlebody is pushed in slightly as the Haggard splitting, and then we're going to take the bridge number of knots with respect to that Haggard splitting. And so kind of as an abuse of terminology here, we say that if the knot is actually parallel, is isotopic into the Haggard surface, then it's bridge number 0. And it turns out it's not hard to see that the examples that Berge gave of knots that admit non-trivial surgeries that give you handlebodies back again are 1 bridge in this sense. Okay. So this was kind of an important concept towards classifying certain knots that admitted at least solid torus surgery. So Gabai showed that if you have a knot in a solid torus, so a handlebody of genus 1, and it admits solid torus surgery again, then in fact that knot is one bridge, at most one bridge. It could also be zero bridge. And then once, well, then Berge gave these examples of one bridge knots in solid tori that admit solid tor surgeries, and you could see that, well, these one bridge knots that Gabai was talking about were exactly the Berge type, and so then you could classify exactly which of these knots, what the one bridge knots were that admitted these solid tor surgeries. So that's kind of the theme. You bound the bridge number and then you classify the knots with that property once you know they're one bridge knots or something. You have a bound on the bridge number. More generally, I want to talk about surgeries giving you boundary reducible manifolds. And so a three manifold is boundary reducible if it contains a properly embedded disk which is not boundary parallel. And so for example, handlebodies are boundary reducible manifolds. And then Ying-King Wu in the early 90s showed that, well, if I have a knot in a genus G handlebody that's not parallel to the boundary, and it admits a handlebody surgery, or boundary reducible surgery, in fact, that the distance between the surgery slope and the meridian is 1, so it has to be an integer surgery. And the way he proved it was, well, you have a knot in the handlebody, and you have after surgery, you have a boundary reducible manifold. So you look at a meridian of the handlebody restricted to the knot exterior. That's a punctured disc in the knot exterior. And then you look at a boundary reducing disc after the surgery, and that's a punctured disc in the knot exterior. And then you look at the intersections of those two surfaces. You analyze the intersection of those two surfaces, and then if the distance was at least 2, you could see that the knot is one bridge in the handlebody. And then, knowing that the knot's one bridge, he looks at, well, what are the one bridge knots that have a distance at least 2 surgery that give you a handlebody back again? And you could see that, well, in fact, they had to be zero bridge. So it's the same kind of argument. You bound the bridge number, and then you classify those bounded bridge number knots that have that property. Wu also showed that if you have a satellite knot in a genus G handlebody, and it admits any surgery that gives you a handlebody back again, then in fact it's a one bridge knot. So with these kind of with these arguments and this result in the air, he conjectured that, in fact, if you have a knot in the handlebody that's such that it admits a non-trivial Dehn surgery, which gives you a boundary reducible manifold, then in fact the knot is zero or one bridge. I think really, Berge and probably Gabai also asked this, but it's hard to trace that. But anyway, Wu actually said this in a paper. So actually in 2013, not 2015, Sean Bowman gave counterexamples to that. He gave examples of infinite families of knots in a genus 2 handlebody that were hyperbolic knots and that admitted non-trivial Dehn surgeries that gave you the genus 2 handlebody back again. And so they're hyperbolic, so that means their exteriors are irreducible, boundary irreducible, atoroidal, and anannular, and most importantly, the bridge number was bigger than 1. Well, so that ended that, but you still wonder, at least I still wondered, well, maybe there's some bound on the bridge number, so maybe this kind of argument might still work. You put some bound on the bridge number, and then you work from that. So that brings us to today's talk. So Sean gave lots of examples of knots in genus 2 handlebodies that admitted handlebody surgeries, and only some of which he showed were bridge number bigger than 1, certain families. So today I want to talk about using a different technique to show that the bridge number is bigger than 1 for other families that he constructed, and in fact show that the bridge number gets arbitrarily large. So at least on the face of it, this kind of scheme for trying to classify such surgeries might not be fruitful. And then So I want to show that some of these families of Bowman's knots and genus 2 handlebodies have arbitrarily high bridge number. And then I also want to give examples in higher genus handlebodies where these knots in higher genus handlebodies that admit handlebody surgeries that have arbitrarily large bridge number. And again, in handlebodies of arbitrary genus, I want to give some examples of boundary reducing knots that admit boundary reducing surgeries but not handlebody surgeries that again have arbitrarily large bridge number. Okay, so to describe the boundary reducible manifolds that are not handlebodies, I need to talk about a DPQ Seifert space. So a DPQ Seifert space is just going to be a Seifert space over a disk with two exceptional fibers of order P and Q. And so that's a manifold with a torus boundary. And then if I attach G minus 1 handles, I get a manifold with genus G boundary that's boundary reducible. And those are going to be the boundary reducible manifolds we get for this talk. And so the result is joint work with Mark Baker and Sean Bowman. And that is...
You said Mark Baker.
Oh, I'm sorry. Ken Baker, Sean Bowman, and me. Yes, sorry. So let G be bigger than 1. Then for any positive integer n, the following hold. There are infinitely many knots in this genus G handlebody that admit non-trivial handlebody surgeries, and their bridge numbers are bigger than this fixed number n. And there are infinitely many pairs of P and Q such that there are knots in a genus G handlebody that admit non-trivial Dehn surgeries that give you this Seifert space with G minus 1 handles attached and again have large bridge number. That's what I want to show you. The knots in all these families are hyperbolic, so we're talking about hyperbolic knots. So generally, we're kind of sticking to hyperbolic knots because those are the generic knots. You know, it's like Wu's result about satellite knots. You know, when you have a non-hyperbolic knot, usually they're special. You can use something that's special about them to just say something more. So usually you want to think about hyperbolic knots as kind of the generic category. So these are all hyperbolic knots, and then we can see that there's only one non-trivial surgery on each knot, which yields a boundary reducible manifold in this case. Furthermore, I think it was Yi was pointing out the surgery dual of a knot. When you do Dehn surgery on a knot, the surgery dual is the core of the attached solid torus, and you can see that as a knot in the surgered handlebody. So when you have a knot in a handlebody that admits a Dehn surgery that gives you a handlebody back, then the surgery dual is another knot in the handlebody with the same complement. And so you might ask, well, are they the same knot? And for these knots, you can often see that just the bridge number of the knot and surgery dual distinguish the knots. Okay, so let me talk about the construction of these knots. So let T be a once punctured torus and tau be an essential simple closed curve in this torus. Then I want to look at the genus 2 handlebody I get by taking that one punctured torus cross I. And then tau, this simple closed curve, simple closed curve in T becomes a knot in this handlebody, this T cross I, which we denote by k sub tau. And then we're going to frame this knot by using so we're thinking of the tau as being a simple closed curve in the middle level of this product, and then we're going to frame it by T cross 0. That lets us take coordinates, to use coordinates to describe the surgery, and so in particular, the 0 surgery on k sub tau is a handlebody. It's this genus 2 handlebody back again, and that's easy to see because I mean, certainly the knot's parallel to the boundary, but in fact it's a core of that handlebody. So any Dehn surgery on that knot is going to give you a handlebody back again. The reason why we're looking at the 0 surgery is that So after the Dehn surgery, the torus in which tau sits, you're doing surgery along the slope of T, and so along the slope of that once punctured torus. So when you do the surgery, you're capping off that framing curve coming from the boundary of the punctured torus with discs, so you get that torus becomes a disc. And so you can see after the zero surgery on case of tau, at least the boundary of some meridian disc. It's simple in a certain way, and in particular it's going to be simple with respect to a different fibration we're going to take of H. So that's why the zero surgery in particular. So let me be a little more specific. I want to coordinatize the torus T. So let lambda and mu be two kind of framing curves for this torus T, where I'm taking T cross I. So that gives me a meridian and longitude for this torus, or a basis for the first homology of that torus. And then I want to take I want to construct this three-punctured sphere, P, by taking the neighborhood of the longitude at the first level and a neighborhood of mu in the bottom level, and then banding them together. So that's a three-punctured sphere on the boundary of this punctured torus cross I. And then, in fact, you can fiber you can refiber this handlebody as P cross an interval. So I can rewrite this handlebody H, which is T cross an interval, as P cross an interval. And it's with respect to this fibration, writing H as P cross I, that the boundary of this meridian disk under the zero surgery is nice. So here's a picture that Ken Baker did. And so here, this is P cross I, the fibration P cross I, and here's this is supposed to be the middle level torus in which the knots that we're going to be talking about sit. So there's simple closed curves in this middle level torus. And so the boundary of that middle level torus is nice with respect to, remember that's going to become the boundary of a compressing disc after I do the surgery. So that's nice with respect to this P cross I fibration of H. Here you can just see here's the meridian curve, here's the lambda curve in this kind of picture. All right. So let me be more specific. If we can, so we have these simple closed curves, essential simple closed curves in T, and I can write them as P times mu plus Q times lambda. And so if so, I'll denote that by tau is equal to tau PQ. And then, as Ken was saying, we refer to that knot in H as a PQ lashing. So you might remember that this is a curve, an essential simple closed curve in that torus, and the knot. Thinking of that as a knot, you can kind of think of it as lashing these posts in the P cross I. And as Ken also pointed out, when you do the zero surgery on this K tau, where tau is this PQ curve, you can rewrite that with this surgery description. It's surgery on the three different boundary components of P. It's +1 surgery on the outside boundary, and then P over Q minus P, Q over P minus Q surgery on the inside boundaries. Okay. Well, of course, those aren't the knots that we're going to be talking about, because they're all boundary parallel. In fact, they're cores. But so I need to use that to construct these non-boundary parallel knots that emit handlebody surgeries. To do that, let me remind you of something that Ken was talking about. If you have a handlebody, you take two curves on the boundary of that handlebody. They're said to be jointly primitive if there's a meridian disk. If there are two meridian disks such that the first one intersects the first curve and is disjoint from the second, and the second disk intersects the first curve in a single point and is disjoint from the second. So jointly primitive, you should picture two different cores of the handlebody. They're sitting on the boundary, but they're two different cores in the handlebody. A curve on the boundary is disbusting if it intersects any, and the curve on the boundary of a handlebody is disbusting if it intersects any meridian disk in that handlebody, and it's indisbusting if it intersects any meridian disk at least n times. And then it's a curve is annulus busting if it intersects any annulus properly embedded in the handlebody at least once. Okay, so let P prime be a three-punctured sphere in the boundary of a genus G handlebody, and I'm going to denote its boundary components as A, B, and C. So you call the pair handlebody three-punctured sphere P prime a strong handlebody pair if two of the curves are jointly primitive, and then the third one is three disbusting and annulus busting. So that's supposed to be thinking about this picture. So you can ignore the parameterizations here, but this is A, B, and then C. And these A and B are jointly primitive. This C is not three disbusting, certainly, but what I want you to picture is applying the homomorphism of the boundary that's Dehn twisting in this complicated curve. And that's going to, and look at the image of this three-punctured sphere under that Dehn twisting. Then the result will be, the C curve will be three disbusting and annulus busting. And then you call a pair a strong Seifert pair if, two of the curves are parallel on the boundary, and each one is primitive. So this is an example. And then C, the third curve, is disbusting and annulus busting. So again, you want to take this C and then apply a Dehn twist in this complicated curve. So those are some examples of a strong handlebody and strong Seifert pair. So let's see. Let me just point out the gamma 2 curve is complicated in the sense that it's disbusting and annulus busting. And so if you Dehn twist enough times, the curve C will also become three disbusting and annulus busting. You have to show that, but that's believable. And then more generally, we can get examples of such pairs in a genus G handlebody by taking the same pictures for the three-punctured sphere, but by taking a disbusting and annulus busting curve in the genus G handlebody and twisting along that. Again, such a curve that's disjoint from A and B. So there are examples of these pairs, lots of examples of these pairs. And so, how are we going to construct the knots that we're interested in? Well, we're going to take this P cross I, our small handlebody H with the knots in them, and we're going to glue them on in this complicated way onto the boundary of a genus G handlebody, either along a strong Seifert pair, or three-punctured sphere, or a strong handlebody three-punctured sphere. And then, so I've taken P cross I, glued onto this genus G handlebody. So I'm thinking of H, that P cross I is a small handlebody, and I'm gluing it onto this handlebody, and I get a big handlebody M. So M is the result of gluing H to H sub G along this punctured, three-punctured sphere. And so that I'm going to refer to as M, and it's either going to be a strong handlebody or strong Seifert type, depending on what kind of three-punctured sphere I glued H along. Okay. So then, because this three-punctured sphere is complicated, it's going to bust any kind of special surfaces in the complement of this knot sitting in H. So once I glue on, so I'm going to take H, glue it onto this H sub G along this complicated three-punctured sphere, and then the knot K sub tau becomes a knot in this big handlebody. And I'm claiming that, well, because we glued along this very complicated three-punctured sphere, the resulting knot will be hyperbolic. Its exterior will be irreducible, boundary irreducible, atoroidal, and anannular. And again, that's because we chose a complicated three-punctured sphere to glue along that busts up any special surfaces. So now let's see that, well, if it's a strong handlebody type, I would take k tau of strong handlebody type. K tau is in this knot of strong handlebody type. And I take the zero surgery on k tau in this big handlebody M, then I still get a handlebody back again. And that's this picture. So remember, we're taking this, supposed to be picturing this P prime is this three-punctured sphere that's of strong handlebody type. So A and B are jointly primitive. And then C is this complicated curve that I get by Dehn twisting along gamma G, this disc-busting curve. And so remember that, well, zero surgery on H just has this very simple surgery diagram by surgeries along, just corresponds to surgeries along the boundary components of P. And so I get a +1 surgery along this curve C, twisted many times around, and then I get P over Q minus P and Q over P minus Q surgery on these core curves. So remember that we can forget about, when we're just thinking about the homomorphism type of the boundary, we can forget about the surgery here because it corresponds to a 1 over n surgery on a knot that's parallel to the boundary. So I just end up with surgery, these two surgeries on these core curves, which will certainly be a handlebody. So it's not hard to see that these are knots that give handlebody surgeries. These are hyperbolic knots that emit handlebody surgeries. Similarly, if I have, if M is of strong Seifert type, so that means I'm gluing H along this three-punctured sphere that's of Seifert type, then, and tau is tau PQ, then zero surgery on K tau is this Seifert fiber space over a disk with two exceptional fibers with one handles attached. And so that's this picture. So remember, this is kind of a typical, well, at least these are the Seifert pairs we've been looking at. So I have A and B, they're parallel on the boundary, and they also represent primitive curves. And then I have this complicated C. But then when I glue in the handlebody P cross, when I glue in a P cross I, and then I look at the surgery along the corresponding K tau, then that is the same as doing surgery on these boundary components of P prime. So I have P over Q minus P surgery here, Q over P minus Q surgery on this boundary component, and then +1 surgery on this twisted component. So again, I can forget about the complicated curve and the +1 surgery, and I'm just left with this picture for up to homomorphism, the resulting manifold, which is, this is going to be a Seifert fiber space. I have these two curves that co-bound an annulus, and I'm gluing on solid tori to the two annuli. So this is going to be this is going to be the Seifert fiber space over a disk with two exceptional fibers with one handles attached. Okay, so this gives us lots of hyperbolic knots in handlebodies that emit handlebody surgeries and boundary reducible surgeries. So for each curve, you just have to pick P prime. There are lots of possibilities for strong Seifert pairs and strong handlebody pairs. So any such choice, and then any simple closed curve tau in the once punctured torus, at least complicated enough, will give you one of these knots, hyperbolic knots. So I need to tell you, well, why is the bridge number getting larger and larger? So I need to talk about that. Well, so I want to talk about the growth of bridge number in the context of twisting along an annulus. That's the way we're going to measure the bridge number here. So given an annulus knot pair in a 3-manifold, so you have an annulus in the interior of the 3-manifold with boundary L plus, L minus, and then I have this knot K disjoint from L plus and L minus, and then given an annulus knot pair, then I can look at the knots I get by twisting along that annulus, and twisting along the annulus. So let Kn be the knot obtained from K by twisting n times along A. That's supposed to be what this is, K sub n. And then, I don't know if this is important, but we can also rewrite this using a surgery description. This is the same thing as Kn is just K, and then I do minus 1 over n surgery and 1 over n surgery along the boundaries of A. Okay, so that's an annulus pair, and then the knots that I obtain by twisting along an annulus pair. And then I want to describe define a catching surface for an annulus pair. So a catching surface for this annulus pair in N3 is a properly embedded surface in the manifold N. Well, actually, it's a properly embedded surface in the exterior of the link L plus, L minus, and K. So in the exterior of this link, with the properties that this surface Q intersects the boundary of L plus and L minus. So those are the boundaries of the annulus in coherently oriented curves. So if you orient the surface and you look at the induced orientation of the boundary, all the curves on the boundary are in the same direction. And furthermore, that the slopes of the boundary components are different from the slope of the annulus A, that the annulus induces on the boundary. So that, and then I also need to know that it has a non-empty intersection of the boundary of Q with in the neighborhood of L plus and L minus. So that's a catching surface. And then Ken Baker, Cameron Gordon, and I showed that in this context, so if I have an annulus knot pair in this manifold N, and you have a Heegard surface for N, and I can measure bridge number with respect to this Heegard surface for N, and if this knot pair is catching, in the sense described above, then the bridge number of Kn has to go up, unless well, kind of the two obvious things happen. Either the annulus is actually isotopic onto the Heegard surface, in which case you're getting Kn by just twisting along the Heegard surface, and you're not increasing the bridge number, clearly. Or K could be isotopic to be disjoint from the annulus, in which case twisting along the annulus isn't going to change the isotopy type of the knot. So if those two obvious things don't happen, then the bridge number has to go up. And so the idea is, where the catching surface comes in is you use the catching surface to give a lower bound on the bridge number for a large enough N. So the Euler characteristic of this catching surface gives you a lower bound on the bridge number. And N. So then you can see that the bridge number has to go to infinity. So hopefully I'll have time to talk a little bit about how that argument goes. But having done that, then we can use that to see that, well, these knots have arbitrarily large bridge number. We just need to see these knots as twisting along some annulus pair. And that's not hard to do. So let's see. If I have alpha is a curve in T, and then kappa is also a curve in T, if let tau, kappa alpha n be the result of Dehn twisting kappa along alpha n times. So that's this picture. So I'll denote such a simple closed curve in the torus that can be described that way as tau kappa alpha n. And then, then I can see in the context that we've been talking about, I can see my k tau alpha, my k tau kappa alpha n as coming from an annulus knot pair. Namely, I take alpha cross. So remember, I'm looking in H, which is T cross I. So T cross minus 1 to 1, and then I'm going to look at alpha, the annulus I get by taking alpha, the curve alpha across minus 1/2, 1/2, and then kappa is this other curve in T, and then tau kappa alpha kappa n is just the, if I look at the corresponding knot k tau in H, I just get the knot that I get by twisting k kappa along A alpha n times. So anyway, the knot k tau can be looked at as gotten by twisting along this annulus in H. So that sets it up to apply the argument that I just described earlier. First, you have to rule out the existence of, so I have this, so these knots that I'm interested in that emit these non-trivial handlebody surgeries can be thought of, or at least a class of them can be thought of as twisting along some annulus. So if I want to see that the bridge number goes up, I have to show that that annulus doesn't lie on the Heegard surface of the ambient manifold. Now again, remember the ambient manifold is the big handlebody. And I also have to show that the knot's not disjoint, can't be isotoped to be disjoint from that annulus. So again, that's just a property of the fact that we've glued. So remember, the big handlebody is this P cross I glued onto the handlebody in this H sub G in a complicated way. So, so for example, to show that there's no annulus disjoint from, no annulus between the boundary components of A alpha that's disjoint from K kappa, that's just, you say, well, the thing I'm gluing along is so complicated. If there was such an annulus that lives, the boundary lives in H. If the annulus, if there was an actual annulus living in M, the three-punctured sphere is so complicated that it would have to bust that annulus. It would have to, that annulus would have to live just in H, and then it, and so you'd have to see it in H, and when you look in H, you see there's no annulus between L plus and L minus that's disjoint from K kappa. Well, anyway, it's just using the fact that you're gluing along a complicated surface guarantees these two conditions. And so we know that the bridge number has to go up for at least this class of curves if, as long as there's a catching surface. So I have to show you the catching surfaces, and this will give an example of a catching surface. So here, this is supposed to be, remember, so I'm going to do this for these examples that I've been discussing. So I have this three-punctured sphere, which is of strong handlebody type. So remember, I get it by taking this, this simple annulus of handlebody type and Dehn twisting along this gamma G. And so the catching surface is going to be the one that I get by taking this meridian disk. Remember that the link alpha and kappa, or K alpha, or at least the A alpha and K kappa, live in this in the punctured sphere that I get by gluing in P cross. They live in P cross I that I glue onto this three-punctured sphere, and you can see that it's not hard to see that the intersection number of the boundaries of A alpha and kappa, or at least the boundaries of A alpha, are, the intersection number with this disk is non-zero when I glue when I glue the knots, when I look at the knots inside this neighborhood. And so I can just restrict Q to the exterior of that link, the boundary of A, of the annulus, and the boundary of K, and then I can start tubing along. Remember that a catching surface has to have only coherently oriented curves along the boundary of L1 and L plus and L minus. So I'll just tube boundary components that are oppositely oriented to get my catching surface. And then because the intersection number was non-zero, I know I'll have some boundary curves left after I tube oppositely oriented ones. So I get a catching surface for this situation, and then the previous theorem shows that the bridge number has to go up for these knots. So that's basically the argument. I'd like to just kind of give you a sketch of how do you prove something like this, that the bridge number has to go up in this context. So I want to talk a little about the argument of Ken Baker and Cameron Gordon. So let's see. So I want to sketch this argument that the bridge number of these knots that I get by twisting along this annulus, when I have this annulus knot pair, have to go up. Well, remember what we have to do is we want to show that the bridge number goes up, or these two kind of trivial things happen. The annulus was isotopic into the Heegard surface, or the knot could be isotope disjoint from the annulus. So let's assume that there's a bound on the bridge number for all Kn, C, and we want to show that these two kind of trivial situations have to arise. So let's see. So the first thing to notice is that this twisting along A induces a homeomorphism of the exterior of L plus, L minus, and K with the exterior of L plus, L minus, and this K sub n, which I'll call X sub n. Okay? So you mean twisting along the annulus in the exterior of L plus and L minus gives me a map of the exterior of L plus and L minus to itself, and you can see that it takes K to Kn, so it restricts to a map of those exteriors. And then this homeomorphism, this twisting along A, sends Q, I mean the catching surface Q, to a new surface in this picture that has boundary that's kind of twisting along this annulus. So I get this, the image here of Q sub n, is complicated kind of longitudinally. It's twisting more and more times this way. So let the boundary of this exterior be a boundary of the handlebody, and then T plus, T minus, and Tk are the boundaries of corresponding to L plus, L minus, and K sub n in the knot exterior. And then we have this, remember we have this Qn, that's the image of Q under this homeomorphism. And then, so now I want to calculate the bridge number. I want to look at the bridge number of K sub n. So let S hat be a Heegard surface, and then let S be the restriction of that Heegard surface to the exterior of this link. So I'm just, I have a punctured Heegard surface now, the complement of L plus, L minus, and K. And then kind of the main properties that I want you to focus on here. So this is just a brief argument. I'm just trying to give you the idea, but the key properties are the following. The Qn, if you look at the boundary components of Qn along Kn, they're meridians, as are the boundary components of the punctured Seifert surface. So boundary components of Qn and S are both meridians on the on the boundary component of Kn. So I can make sure that those are disjoint, they don't intersect. On the other hand, the boundary components of Qn and S intersect more and more times on the other boundary components, on the boundary component of L plus and L minus. Because remember, the boundary components of S, that's this punctured Heegard surface, so that's just meridians of L plus and L minus. But the boundary of Qn was gotten from the boundary of Q by twisting along this, vertical surface. The annulus. And so the intersection number of these boundary components is getting larger and larger as n goes to infinity. And the boundary components, there's no intersection between the boundary components of Qn and S along K, or Kn. And at the same time, the Euler characteristic of Qn is independent of n, and the number of boundary components of the punctured Heegard surface, at least those coming from K, is bounded by this number C. So again, we're going to look at the intersections of these two surfaces in the exterior of this annulus pair. And, a thin position argument of GABI, if you kind of apply it in this context, says that, well, as long as A is not isotopic into the Heegard surface, then we can guarantee that these arcs, we can find a level Heegard surface so that the intersection of the punctured surface with Qn are essential curves in Qn. So that's where the first trivial case could pop up. We're going to assume that, well, it's not isotopic into the Heegard surface, and then the intersection of these two surfaces are in essential arcs. And so So we have this picture. So let V plus be the boundary components on Qn and on S coming from T plus, you know, the neighborhood of L plus, and V minus be the boundary components coming from T minus. And then we have these others that, and remember the intersection number of a component of V plus on Qn with V plus on S is getting larger and larger. So we're going to see more and more arcs of intersection emanating as n gets larger and larger from these vertices, or these, not vertices, but these boundary components. And we see no intersections between the corresponding boundary components that lie on K sub n. So, you know, you're getting these boundary components with larger and larger valence as n goes up of essential closed curves. So eventually, I mean, the valence, we don't know how many boundary components V plus and V minus has, but what we do know is that the valence is going up on those. And otherwise, the Euler characteristic is bounded between Qn and S as n goes up. So that's saying that kind of the topological type of these surfaces is remaining fixed, whereas the valence of these things is going up. So eventually, you just argue that you have to get two arcs of intersection that are parallel on both graphs. They're parallel here, and they're parallel there. And then that gives you the annulus that we're looking for. If you, so here's E1 and E2 are these arcs of intersection that are parallel on Qn, and here's Fs is the disk of parallelism between E1 and E2 on S, and so when you take their union, you get this annulus picture. You have this, I mean, this is supposed to be S, here's the disk between E1 and E2 on S. The disk F sub Q between E1 and E2 lies in Qn, which is this vertical surface, so it looks like this. So it gives you an annulus. So that's where the annulus comes from, and this annulus, because it lay in the complement of K in this S hat, so it lay in you know, in S, which is, you know, which is the complement of K in particular in which is the complement of K and S. Well, anyway, you see the punctures of K. You see where K intersects these surfaces when you're doing this analysis. These disks do not involve those punctures, so they're disjoint from K. That's all I'm trying to say. So this is an annulus disjoint from K, which is what you were looking for. Okay, well, that's just kind of a quick sketch about how you'd go about proving this bridge number calculation. And so, again, I'm just left with the same question I started with. What are the knots in a genus G handlebody that admit handlebody surgeries or boundary reducing surgeries? And I guess I don't have more to say about that. But I would point out that all of the knots that we have, that we construct here, have one boundary reducing surgery. According to Wu, there could be two non-trivial boundary reducing surgeries. And so presumably the knots, we don't construct any with two non-trivial surgeries, but I'm sure there are, and they may be more special. So maybe at least there's a chance of showing that they're one bridge, for example. Okay, well that's it.
Are there any questions?
So you said the bridge numbers of the dual knot and the original knot could be different. So is there a linear bound between them?
In the difference between the two, a linear bound?
Yeah, for example, a linear bound of one bridge number in terms of the dual.
I don't know. I don't know if there's a bound at all. So that's a question. That's a good question. So the question was, is there a bound on the, you know, if you know the bridge number of one knot, do you have a bound on the bridge number of the dual? And we don't know examples where the bridge numbers of both kind of go up. And I guess, so that's one thing. And then you're saying, even if they do, maybe there's a bound in the distance between the two. Is there some relation between the, sorry, the bridge numbers of the two? Yeah. Yeah, I don't know. I don't know.